to all present you over here. And I am really grateful and honored to be selected by Taiwan Surface Finishing Association for giving me the opportunity to speak about these processes which we have developed in India. I must be thankful to all the supports I have got from Industrial Technology and Research Institute colleagues, Bruce, Jennifer, and so on and so forth. Really, it is highly admirable. Thank you. So we start with our topic today. Say no to cyanides to electroplate bus bar. So we are all aware of it. The issues are related to the cyanides. So whole world is looking for the suitable and sustainable options for replacing the cyanides from any of the processes wherever it has been used traditionally. Well, can you go to the second slide, please? Okay, so my today's talk will be outlined as our company, a little bit company introductions, reasons for plating, different plating options, and options. Whenever there is some option, there are some issues as well. So we'll highlight some of the issues and the option for the newer hazardous-free chemical options and its sustainability, and which will have followed by a summary slide. Okay, our company is situated in Mumbai, head office in Mumbai, and factories at different places, and we have 5 verticals. And this is actually born in 1957, so more than 5-year-old company with 76 million sales USD sales turnover, with 35% market share for the GMF range of chemicals, and we are ISO 9100 certified company, and more than 1100 employee and associates working with us. This is the different verticals. You can see it, 1957, the chemicals, it was the cash cow of our group. And then we started in 1964, engineering divisions supporting to the electroplating and associated waste treatments and also different associated processes. 1994, we acquired a paint company as you can say that related diversifications, and also we introduced lubricants associated with the metal finishing, and of course we have a real estate division. So we have a beautiful mall in Mumbai. Some of the photographs of our different chemical manufacturing company, you can see it, the front view of our Dadra plants and inside the reactors. And then on the right side, you have Jammu factory where we produce different chemicals for metal finishing products. Well, this is our paint division plant. It is left side, it is in Dadra, that is western part of India, and the right hand side, the plant is in northern part of India, it is in Borottiwala. This is our engineering division on the left side, and on the right side you will see the lube division. These are our plant manufacturing plants. Well, we have, as I said, that more than 1100 direct and indirect employees, but direct payroll and some skilled personnel. If you talk about it, will be 900 the technical person and 200 in the support functions. More than 70 people working in R&D and QA for process development. This is a short introduction about our company. Next, please. We have 2 overseas office in Thailand and Bangladesh, and we have different channel partners, both India and global supply chain position. Okay, so this is about our company background. So I'm moving forward to the next slide. So this will give us a little bit, background about the bus bar, what it is, and where it is being used. All of us are aware that bus bar is a metallic bar in a switchgear panels, which is actually, passing the current from incoming feeder to outgoing feeders. So in simple terms, that the bus bar actually carries the currents, and most of the bus bar, the MOC is copper or aluminum. The purpose of, we are aware that it is passing the current. So if there is an oxidation of metal takes place, it will increase the resistance. So we need more power, more voltage to pass the same current, and it will result in the higher temperatures. It will increase, carrying capacity will reduce. As a result, we will see some of the corrosion taking place, and it will reduce the integrity of the conducting surfaces. So to resolve this, one of the good option is to apply some of the coating materials for its longevity and sustainability. Let's see what are the options for plating. So it will be copper, silver, tin, depending upon because that's whatever coating we will be applying it should have good thermal conductivity. That is the most pertinent choice for the coating. So best in line will be definitely silver. Some cheaper substitute are also doing only tin plating and with an undercoat of copper. Let's see about the processes, what we do you can see some of the photograph of the plated components, and you see this is the normal process sequence we industry use for plating on busbar while doing copper tin plating. Now obviously starts with the soak cleaning, specialized soak cleaning, so that it doesn't age the base material aluminum. Then we have an etching, then zinket 1, then desmitting, and then we have zinket strip, and so on. Coming back to zinket 1, then zinc strip, then zinc 2, and then try copper coating, and then tin plating, and then we have neutralization and passivation and dry. So this is the process what we copper tin coating on aluminum busbar. Here this will have a copper silver. So most of the up to the copper more or less similar, and thereafter instead of tin they goes to the strike silver, main silver coating, and then followed by anti-tarnish and so on and so forth. This is the basic outline about the process sequence. Now let's see the challenges. Well, this is if all of us are aware that in these processes like zinketing, copper, and silver, in all the process contains traditional processes contain cyanide. So our task here is to replace cyanide for all the associated processes, and so that we can make our entire process cyanide free. At the beginning, the challenges in this approach was the first and foremost to find out a suitable substitute for cyanides, because all of us, we are aware that cyanide is well established ligand, and it gives a very stable complexes with most of the metals. Silver being so much noble, positive 0.8 its standard electrode potential. So thermodynamically it is very, very noble. But if in presence of cyanide, it forms silver cyanide as a complex, and its log K value is around 21. So this provides a very stable complex, and over the years it is totally established and people know how to use the cyanides, but we all know the issues associated while using cyanide. The choices for replacement of cyanides, we were considering in our company too, that the complex should be, or ligand should not be toxic, and it should not create very harmful breakdown products, so that the subsequent waste treatments of the generated waste would be easily treated and recycled wherever it is possible. So these were our basic approaches. So starting with the zinket coating, conventional technology, as I said, that it contains cyanide as a complexing agent, so to hold this alloying element, for example, iron, copper, in the solution. Because we are all aware of it, the zinket coating is in alkaline. In the alkaline media, these comparatively noble ions like iron, copper, etc., tend to get precipitated out. So therefore, the cyanides are used as a stabilizing agents and make it all in complex form. So traditional process contains mainly the constituent is zinc, caustic soda, NaOH, cyanide, sodium cyanide or potassium cyanide in the formulation. As a result of this zinket coating, when we apply on aluminum, we will have a zinket top coat, which will be either zinc iron alloy with zinc approximately 97% and iron will be approximately 2%, or zinc copper 86%, zinc, copper is around 14%. This is normally the composition of the coating of the traditional processes. But what we have done it over here is we have removed the cyanide from the usage. Instead of cyanides, what we have done, we have used some ligands like organic, non-cyanide organic complexing agents, mainly dicarboxylic acid, or maybe more than even carbon atom is also there. So let's say quadra or hexacarboxylic acids, and some cationic polymer and some multication. So here you can see in the conventional process we were doing alloying element with only iron or copper. In case of newer technology, we are using nickel, copper, and iron along with the zinc. So it is a tri-alloy zinket, and with a composition of zinket coating is approximately 80% of zinc, and nickel is around 1.6%, copper is around 16%, and iron is around 2.5%. Formulations are very stable with the composition what I told you. It provides lesser or less aggressive attack to the base, and therefore the thickness of the zinket coating after, let's say, double zincate, we get approximately 0.26 micron at 2 minutes of zincate coating. So more thinner deposit and more compact as a deposit. It helps for the subsequent deposit addition. Furthermore, being a true zinc alloy, consisting of nickel, copper, iron, as compared to the traditional processes, binary alloy, zinc and iron or zinc and copper, this is fairly less corrodable. For example, if we go from the zincate to subsequent coating processes, this solution, this deposit has less tendency to strip off in the contact surface or contact solution, component touch surface. So it improves or it ensures the subsequent deposit adhesion. So with the newer technology, we can get better adhesion. So subsequent failures like blisters or peeling off gets reduced. Okay, so this is the ACM photographs of zincate coating. So this whatever you are observing on the screen is aluminum surface and followed by only zincate coating. You can see there are a lot of pores on the right hand side deposit, whereas in the left side the deposit pores is much lower. So the left side coating is containing alzincate MB and C. So that is the non-cyanide based alloy zincates. Okay, moving forward from the zincate coating to copper coating. To copper coating, once we are talking about, we know that there are three processes, let's say cyanide, acid and alkaline. So on zincate coating, it is obviously the choice is alkaline ones, like either cyanide or alkaline. Now with the different options of copper coating, we have some issues. For example, in case of acid coppers, copper remains as +2 state, and copper has got electrode potential is copper plus copper 2 to copper iron is plus 0.34, whereas iron is minus 0.44. So thermodynamically, copper is less active than iron. So therefore, there is always chances of getting copper metal deposit on the MS. So this gives you immersion coating, and which is not very stable or which is not adherent to the base. Yeah, after deposit, if I just scratch it, something like that, that coating gets peeled away. So this is an issue. Therefore, on directly component like MS, the acid copper cannot be used. Whereas when we talk about cyanide or alkaline copper, metal remain in the complex form, not remain as only single Cu plus state as it is in the acid copper. As a result, it changes the potential value. It makes it more conducive for plating, and we don't get addition on the bases. Particularly on aluminum one, we talk about it. So if we use either cyanide or alkaline copper, it doesn't give much issues as far as metal precipitation or immersion coating is concerned. So eventually we get an adequate strike coat or base coat for subsequent deposition. Now we are not talking about cyanide copper. However, the cyanide copper is well established. We are all aware of it. So what are the options? We have pyrophosphate based copper and we have a phosphonate based copper. Now both processes has got some advantages and disadvantages. Now let's see the complex what we form, copper pyrophosphate complex. You can see the complex on the right hand side. It is the copper pyrophosphate complex. It is stable at 8 to 8.5 pH, and copper remain as we discussed. Copper remains in the complex form. Now it has got a fantastic covering property. You can see this is the faucet components, and you can see the coverage in the inside, because we are aware of it that the inside there is no possibility of an anode. But adopting copper pyrophosphate, we can get a best coverage. You can see the faucet component here as well, which is after with pyrophosphate copper, then nickel and chrome plating is done. So if we see on the LCD portion, in case of with pyrophosphate, we get a much better finish. So this is one of the greatest, this property which pyrophosphate offers. But pyrophosphate associates with some of the issues. For example, pyrophosphate is also not very user friendly with respect to the waste treatments. And what the most important thing is that pyrophosphate ion, has got some tendency towards hydrolysis and forming, single uncomplexed copper. So if you have an uncomplexed copper, so there is a possibility that we might get immersion copper deposit, and as a result, we will not have good adhesion. Now, why this hydrolysis takes place? Because in the pyrophosphate complex, you can see there is an oxide linkage over here. This oxide linkage makes the complex little vulnerable towards hydrolysis. Furthermore, as we discussed about a little bit about waste treatment, that concern about eutrophication is also possible. The pyrophosphates are, because it helps to generate the plantation. So if the water body gets contaminated with the more of pyrophosphate ion, there is a possibility that we might get a lot of generation of plants on the upper surface of the pond, so which can eventually take oxygen out of the water and reducing the dissolved oxygen. So this can create problems for water bodies like fish and other elements. So therefore, that pyrophosphates are also not very user friendly. So then our option for the phosphonate based process. Now here you see that it is very similar to pyrophosphate, but the advantage here is we don't have oxide linkage over here as we have seen it with the pyrophosphate ion. So there is no chances of hydrolysis what we have just discussed. Therefore, the pyrophosphate ions are far more stable, and our process is also, what we are talking about is also based on pyrophosphate. So there is, as we said, that there is no chances of hydrolysis. So the solution is much stable and provide a sustainable strike code for on aluminium and or zinc-based die casting or MS components. And the waste treatment is also very, very easy. You have to just increase the pH, and the complex gets broken, and subsequently we can precipitate copper from the solutions. Okay, this is the path parameters shown over here, which on our subject process. And here one point has to be noted, that the process is designed with mixed phosphonate and some organic carboxylic as a complexing agent. This makes this process as a second generation system. In the first generation system, we were having some issues about very, very low thickness, and maybe 1 minute 1 ampere per square decimeter, it was to be around 0.12 micron per minute, 1.5 ampere per tm square, whereas now we can get it around 0.3 micron per minute at 1.5 ampere. That's the one advantages. And I will show you one more advantages when we'll see the cross-cutting photographs of a heat-treated aluminum busbar components. So please keep your enthusiasm still there. So I will discuss that point of time. So this is one advantages, and we need to maintain this metal to complex ratio is 1:10:20. So the very excess amount of complex is also not desirable. So we should maintain somewhere between 1:10:20 time ratio. And another important thing is that we need to use oxygen-free high conductive copper anode in place of normal electrolytic copper anode, which is popularly used so far with the cyanide-based system. Okay, this is the Hull self-test results of cyanide versus superite NC. We have to tell you here that with the alkaline copper, we are bound to get lower thickness. If anybody wants to switch over from cyanide to non-cyanide system, so it is always advisable to increase or create an option to increase the plating time rather than increasing the current density. Current density should not be used much higher. So best in line current density will be 1 to 1.5 ampere per square decimeter. Why we are getting lower thickness is that in case of the alkaline copper remain in +2 stage, and it complex with the corresponding ligand, like in this particular case is phosphonates and some organic carboxylic acids. During electro deposition, copper +2 has to get reduced to copper +1, then copper +1 gets reduced to copper 0 to deposit copper as a metal. So there is a two-step reduction process. Each 1 coulomb, if you pass, it actually 50% of that 1 coulomb, maybe 0.5 coulomb, will be used for only deposition from Cu plus to Cu0. So we eventually will get lesser deposition. Whereas in case of cyanide copper remain in +1 form. So it is a direct one-step reduction. So each coulomb passing of electricity will have approximately twice the rate of deposition in case of cyanide copper. Like here also it can be seen in point number 1. I mean, this is the different points. It can be seen over here. And and this is high current density zone, and this 9 number point is the low current density zone. So each and every point, if you can see, is almost we are getting within alkaline copper, but virtually 50 to 60% less than the corresponding deposit of what can be achieved with the cyanide copper. This is the surface topography of the cyanide versus non-cyanide. Non-cyanide deposits has fine grain with globular, some occasional globular structure, and therefore we get actually a little bit brighter deposit in comparison to cyanide copper. But the deposits are very, very compact. But there is very important that we need to keep desired complexing agent and the ratio of copper to complexing agent. If we use lower, there is a chances of addition failure. If we use more than excess, then it will reduce the rate of deposition, and furthermore that it changes the surface topography also. Now this is the photograph A is with the pyrophosphate based process. You can see this deposit characteristics is non-homogeneous and there are crystal overlapping each other. Now B is with 60 grams per liter of the complex, and the deposits are desired ones, compact and smooth, which you have seen in the previous one with the different magnifications. If we increase the complex, you can see there are some crack develops. As we move on, there are some crack formation takes place, and also deposit becomes more coarser. You have seen it in the earlier slide that there are some fine grain with globular morphology. So if we increase the complex more than desired one, the globular part increases more, making the surface or making the deposit more coarser, and also with forming some crack patterns. If the cracks are more, there is a possibility of hydrogen entrapping more in this particular area, which subsequently could get oozed away and can create some issues. So it is very important that we maintain the complex in the desired level, and it is possible to maintain it because we can analyze this complex by HPLC and maintain the bath in the subsequent in the operating bath without having any problems. We are running this process since 2018 in one of our customers' place for these applications in northern part of India. This is a component, the bus bar up to copper plated, and then subsequently heat treated at 250 degrees centigrade for 2 hours, and then subsequently quenching water. And then the photographs are shown over here. This is with the cyanide copper, this is with the phosphonate copper, and we don't see any blister in both the cases. So we can say surely that there is no chances of any failure in terms of the flick off or peel off or blisters or delayed blisters. Moving from cyanide to next in line process, which is silver. Silver plating, we are all aware of it, why silver plating is desirable. So first and foremost, it is bright, lustrous, and cheaper as well as compared to the other precious metal like gold and so on. So good ductile and very high reflectability. Because of its high negative potential, there's a chances of oxidation is very, very low. So it doesn't form the oxide like normally we see for any coating like zinc on MS, we get a white rust and so on and so forth. So such thing doesn't happen with the silver. So metallic, the coating integrity is much better. It's malleable with high degree of lubricity. So subsequent forming or subsequent applications, this gives more sustainable property to the plated components. We discussed about that it is high resistant to oxidation and also arcing. So that makes this coating very much useful to the components like chip manufacture, like semiconductor and so on and so forth. And of course, it has have the least electrical resistivity as compared to copper and aluminum. This will give us a little bit idea about the evolution of silver coating. It's nothing, as I told you since the beginning of our discussion, that it is a very old process. It is established in 1840 by Elkington's et al. Subsequently, of course, it is based on the cyanides, and we have initially it was only for the decorative application, and subsequently it started using for the functional application also. Obviously, in the solution, it contains potassium silver cyanide. Now, there's a very important thing here is that we need to have a free cyanide. Means there are some cyanides remain as free ions, because in the solution it doesn't remain only as a silver potassium cyanide. Silver potassium cyanide plus potassium cyanide. So that plus potassium cyanide, whatever remaining is that there's a free cyanide. Free cyanide level has to be higher, let's say 120 grams per liter. So to have the proper stability of the solutions, and also less of anode polarization. Otherwise, it creates a plating problem. So in short, what I'm trying to say is, if we use cyanide copper, even though it is very much easy to use, but involvement to the user is very high, because you need to take proper care for while using, and also for the subsequent waste treatment, because the waste solution also will contain a lot of free cyanides or complex cyanides. So that creates a lot of hazards, and ultimately increases the environment footprints. Okay, so there is a strong drive to develop non-hazardous option based on non-cyanide silver to have the green chemistry. Any newer developments associates with a lot of hazards. We are all aware of it. Here also there are a lot of challenges we encountered when we started working on in that's 2015 onwards. First and foremost, that the deposits were unsatisfactory in appearance, even though sometimes we were getting some good results, but it used to get tarnished within no time. That's not sustainable. Electrolyte stability was not good, because the complex which we come, or ligands whatever we tried, it was not stable. We were giving sometime good results, and then maybe that solution next day no coating at all, and yielding to some precipitations and some issues. A lot of difficulty with respect to bath maintenance, very much prone to metallic impurities. What was happening is that we were getting a lot of immersion deposit, because we discussed that silver is a very noble. It can lead to immersion coating to any of the substrates, because in the thermodynamically the silver is more stable in the metallic form. So from silver ion, there is always a tendency to convert it to, or to get reduced to silver zero, so silver metal itself. But these immersion coatings are not very stable, so subsequently leading to the coating failures. Okay, so our strategies were like, as we have been talking about, that should be having a stable silver electrolyte, so that we can use for the commercial purposes, and it should not lead to any harmful breakdown product, which subsequently is very difficult for waste treatment. With the continuous usage, user know how to treat the cyanide-based effluents. Whoever is using, I'm sure all our associates will agree with me that you just remove the cyanides by chlorination, and then it is easy to precipitate the metals. Suppose in place of cyanide, if you use certain ligands, which is forming even more powerful complex, so it is not desirable. That was our strategy. A lot of different ions are tried: fluoride, halides, thiosulfates, which are mentioned in the literatures. We started using succinimide, trithanolamine, thiosulfate. These are also known to the industry, and all the. There are some primary literatures are available, so some informations are there. So we started working on, and we encountered some of the issues with the different processes. We ultimately, those stuffs were not commercially successful. We also saw a lot of issues associated with these processes. Okay, so this is our development in this particular space, and we have developed our own complex. So this process consists of silver in the complex form, and some stabilizers and some conductive ions, and so on and so forth. So it is alkaline, and these complexes, it doesn't create a very powerful complex like if you use any metal with EDTA. So it's very difficult to get rid of metal in the waste treatments. This is the process. The ligand contains nitrogen, carbon, oxygen. So it has got NAG, then O, NCO, then an NAG. So there are different type of complexes. So we'll have some amount of impurity ion and co-deposited ion, for example, carbon, nitrogen, oxygen in the deposits. We'll talk about that. But ultimately, the process is alkaline, cyanide free. is you can use it for industrial as well as decorative purposes. So you can get bright to semi-bright silver deposit. For busbar coating, it is very, very successful. Now we were talking about the complex formations. In the previous slide, we have discussed that there were candidate succinimide. So silver succinimide complex were one of the powerful candidate to replace cyanides. So when we saw it, when the succinimide complex, silver succinimide complex remains in the usage or in the idle time, the succinimide ion tend to get hydrolyzed and decreases the pH. So it forms a little bit acidic residue. So the acidic reaction products reacts with your alkaline material, making the pH total fluctuation. Obviously, the solution will require frequent pH adjustment by adding suitable alkali to maintain the stuff like ammonia and so on and so forth. The stability is a question mark. So therefore, even though it was that time it was a very powerful candidate, now in the modern, the non-cyanide silver formulation, slowly the supply houses started to remove or eliminate that as a complexing agents. We are using a different one, and it is free from succinimide. It gives a much stable complex. And what we have also seen that the tarnish resistance is much better than earlier generation non-cyanide silver processes. And all the associate components are analyzable, so easy to handle, and the silver metal is maintained in the solution by anode dissolution. So operating costs are not huge. Only thing is it is coming from the metal and it is going to the deposit. You need not have to add much of silver containing additive from us. So the operating cost is cheaper as comparatively. Now some of the components photographs are shown over here. This is can be used for all type of components, for electrical or decorative items, for both rack as well as barrel plating applications. So you can see the component of photographs on the left side. It is the with the non-cyanide, and on the right hand side is the cyanide. This is the small pilot plant type operation. But here one thing is important, that after silver plating, one should apply the post dip and followed by the tarnish. This post dip makes the component brighter. Before post dip, the situation is not that lucrative. So you can see that without post dip, the component, the panel looks like, or the component looks like bluish in appearance. But with the post dip, we get brighter in appearance and bright. This is the composition of the solution in comparison to the cyanide based one. You can see that the metal works in the more or less in the similar range. So it doesn't create any additional burden in terms of waste treatment. In fact, it will be much easier than the cyanide based waste treatments. Okay, so we are getting approximately similar rate of deposition as that of cyanides. This is also good for the industry. I told you that the involved additive can be analyzed from the bath and maintained very easily with the desired range. So some of the things are given over here: silver metal by titometry, complexer by titometry, stabilizer by IC. Like here you can see it that we can get a peak profile, and then one can analyze here. And this is by ion chromatography, and brightener by UV visible spectrophotometry, and weighter by surface tensiometer. So we should maintain something like 30-35 surface tension values times per cm, and we get a desired coating characteristics. Whereas in case of cyanide based, the brightness and weighters not very desirable to analyze, and the brightener you cannot analyze. This is some wholesale photograph versus cyanide versus silver. What we have done over here is we checked the deposit characteristics in terms of the color of the deposit, and which is done by the very known test method by LAB test values, the colorimeters like Minolta. I'm sure all of us we know that it is this is the XYZ axis. Now if you go to this side is black, and this go to this side is white. So if the white color deposit will give L value approximately 99 or 100 even, and the black will give you the negative side on this side, and similarly X and Y axis and different shade. So in short, what the value with more or positive L value is whiter in. Now you see in case of cyanides, the L values are relatively on the high CD and LCD is more, more than that of the cyanide-based processes. So therefore, it is actually having more wider. The cyanide paths are relatively more wider. But in case of MCD, medium current zone, the non-cyanide deposits are looking little better. You can see that the same hull cell panels, we have checked the gloss meter at 85 degrees centigrade, 85 degree angle. So we see more or less similar light reflection. So with cyanide and non-cyanide is in the same range. So brightness point of view, I would say that comparable in some cases, even with by altering the brightener part, we can even make little more better. Thickness part also is mentioned over here. You can see that more or less in the same range like cyanide silver. What we have done over here is that we made the hull cell test of a solution which is prepared in the lab, and that solution was maintained for more than 6 months. So time to time we have analyzed this thickness, and it is being presented over here, and also the hull cell characteristics. Now you see this is the initial, this is the front and back side, and after 3 months it is front and the back side. Please make a point that the slight burning on the high CD is tolerable, there's no problem, and it doesn't create any problem as far as the components are concerned while carrying out the actual production. Now here you see this comparative thickness chart, in this case micron per minute. So it is more or less similar and maintained. What we are trying to say that the solution is stable even in idle conditions. Here we'd like to present our analysis about the tarnishing test. Now in this particular case, what we have done it is that 2% yellow ammonium sulfate solution. We have dipped the process components here in the cyanide. You can see it's the before the sulfide test and then the after sulfide test of 5 minutes, and after 10 minutes. 10 minutes, if you get the reduction in brightness, and you get a little bit of hazy coloration on the top surface. But the deposit characteristics of both cyanide and non-cyanides are similar in the dip condition. Now let's see in the second one. Here what we have done the same experiments, but in this particular case we have kept the components in the desiccator with the sulfide solution, saturated sulfide solution in the bottom, so the atmosphere remains with more of sulfur. And we saw that the cyanide and non-cyanide, we don't have much of issue. So what we trying to say over here is that what I told you in the beginning of the process introduction, that our process is behaving almost like cyanide in terms of its tarnishing resistance, which is important for any deposited silver coating. This will give us an idea about different tribological property of the coated materials. Now you see that hardness we have checked. 15 micron deposit with 50 gram loads, non-cyanide silver is harder as compared to cyanide silver. Now here, why question could be asked that why it is harder. Basically, the reason is that we have seen that the coating characteristics, the coating textures, it is the fine grains, even finer than cyanide. So if we have the crystal from crystallized structure smaller, so it will have a compact grain structure, which will result into the higher hardness. And since it is giving you harder deposit, the Taylor test wear resistance is also better. Yeah, and we have seen it 15 micron deposit with 500 gram load with the CS 7 cycle. After 300 cycle of rotation, we can see that the losses is around 16.9 milligram as against cyanide is 20.8. So in terms of Taylor wear index, the non-cyanide deposits are better. Stress of the deposit, what we have seen is that it is much more stressed as compared to the cyanide silver. The reason is that the texture or the deposits are having a lot of voids as compared to cyanide, and then voids, if you see under the TEM analysis, we can see a lot of voids, and that voids are tapped into the deposit, which eventually absorb some of the impurities, for example, hydrogen, carbon, nitrogen, because we discussed about the complexes. So from that complex, we get some nitrogen or oxygen, carbon, and of course from the electrolysis of water, we get hydrogen and oxygen. So there is some trapping. So those impurity stuff also increases the stress, and some of the lattice defects also responsible for the higher stress. So comparatively, what we can see that one negative thing is that with the non-cyanide, it is comparatively little bit more brittle. But the purpose what we are talking about is that let's say the bus bar with up to 20 micron or maybe 25 micron of silver, absolutely no problems. And the customer is in the production scale they're using for last more than 3 years now. Electrical resistivity, of course, with the cyanide, it is again little higher because of the same reason as what we just discussed about. But if we do the heat treatment subsequently, it can be reduced. With the cyanide silver, we can see the resistivity is approximately 2.2 to 2.5 microohm per centimeter, whereas with the alkaline silver, we are getting 3.8 to 4.3. One thing here I would like to mention that the silver, the cyanide silver, I am referring a deposit which is free from any additives. So it is dull and no additive system. If you use organic system, you will be having in this range. But if you use metallic type brightener for containing some selenium, or this will even going closer to this. So this is another important characteristics. But if we heat treat it, and there is absolutely no problem. Here we can see the addition. I will show you in the subsequent slide also. We have checked also the tarnish resistance in terms of humidity testings, and we see normally it is more or less like similar like cyanide. Here we just made some panels with the thermal shocking, and we see that behaves exactly like silver based, cyanide silver. So no problem of blisters and so on. In fact, heat treatment makes it better in the coating characteristics, as it can reduce the hardness and even reduce the stress also. Well, this is the surface topography. This is without any brightening agents, and with the brighteners, what we can say, the very fine and compact grain structure, what we discussed. And in fact, if we measure the grains, it is something varies between 450 to 700 angstrom, as against cyanide silver of more than 40,000. So it's very, very fine grains deposit. And this is after heat treatment, and we don't see any blisters. So this is absolutely what we are getting desirable deposit. This is the panels of the aluminium, and then at a different stages you can see this is the base aluminium, this is zinc-coating aluminium, and then we have the copper-coated aluminium, and then the silver. And then after that we have done the cross sections, and we don't see any gap between the layers. So we are getting desired additions. Here what we have done it is another cross-section figures. Here we have done silver, and this is the copper. You can see the comparison what we discussed in the very first slide of when we introduced our alkaline copper system containing the second generation with the mixed phosphonate ones. You can see in case of first generation, there is a rupture in the coating of non-cyanide copper, whereas with the second generation coat, you don't see such rupture. So I'm sure all of us will agree that if the coating deposition is lower by chance, and that components subsequently if it goes for the heat treatment, so there is a possibility that we might as well that the wrapping can take place on the upper layer of the deposited chrome, and sometimes even it can touch the base material, coating fails. But with the Subright NC, with the mixed phosphonates with some organic acids, such situation will not. Moving towards the last part of our presentations, that we tried to figure out that the tolerance to impurities. We prepare the fresh bath, and we have checked the panels at 0.5 to 5 minutes in Hull cell test, and deliberately we have added different impurities. Here that you can see the effect of copper. This is 5 ppm, 10 ppm, 25 ppm, 50 ppm, and 100 ppm. That deliberately copper was introduced. And what we observed is that bath turns bluish, darker, but the appearance is not changing. So what one interesting thing is that somebody in user level can even identify that the copper, the deposit or the solution is getting contaminated with copper. So as he can see the changes of the appearance of the bath. But the process is having tolerance where the performance is concerned up to 100 ppm, no issue. Here the impact of zinc is shown over here. Here also we don't see much of a defect. Here we show the effect of nickel. Here we find some issues in the MCD zone, and here also the solution is getting pink in appearance. So like we said about copper, it is forming blue, nickel is forming pink. So somebody can even analyze if he doesn't have the adequate analytical tools to analyze the impurities. Now here we can see the effect of aluminium. Again, there is no issue as far as the appearance is concerned, but bath becomes turbid. This one slide can give you the entire spectrum of the effect of impurities. So what we have seen that copper and nickel creates issues, but the solution is having a lot of good tolerance to other susceptible impurities like copper, zinc, even aluminium. So we are coming to the summary slide of our discussions. What we discussed about the availability of commercially successful cyanide-free technologies for all zinc, zincating, copper, and silver. We have not touched upon tin because tin is anyway it is either with sulfate-based system or with a sulfuric acid-based system. So there is no question of cyanides. So with this, I conclude that I guess it will give us a thinking process that we can change or we can say no to cyanide to electroplate bus bar. Thank you very much.